if you can avoid building custom boards,
Right.
that's the smartest thing to do.
Yeah, I definitely I read somewhere, I don't remember where it was, but reproductibility, like being able to replicate something that someone's done is always like the better choice versus, making something proprietary like you
Yeah.
said.
I mean, there's a lot of groups that love to do proprietary stuff because it looks cool.
Hmm.
But the nice thing about using commercial protocols, commercial boards, is that, okay, in 3-4 years from now, people want to upgrade.
Right.
Commercial stuff always gets upgraded,
Right.
it's always supported. Versus if you do something proprietary, it's going to just eat up all your bandwidth and trying to come up with something new or modify something or fixing bugs. So um, that's something that we're trying to push here,
Hmm.
or I'm trying to push. But yeah. Uh, okay, so now I'm going to move off of Dune and talk about another little project, which is that I built. This is a thermal neutron pad detector, and I'll walk you. We have a demo running right now. This is actually installed in a neutron source in Australia, where they're doing small angle neutron scattering experiments. They were using. So this is actually a user facility. It's in a user facility where they're using this SANS technique to look at the COVID molecules, and actually they were looking at lithium-ion batteries, charge, discharge, just to look at the molecular structure of the different materials. So this system here, so this is actually what you're seeing here is the 1 square meter detector which we delivered to Australia. We actually have a 24 centimeter detector that's running right now in the back room. I'll show you, where it's collecting cosmics, neutrons in real time. This board is using an Altera FPGA.
Yeah.
I know you don't like Altera, but I did them. You missed my Xilinx UltraScale Plus before.
It's alright. We
See-
use both.
see-
We actually use both. So
See, so this one had my Zinc UltraScale Plus. That's an amazing change in the technology now with this new SoC stuff. It just opens up so many doors in what you can do. It's amazing. So this is a helium-3 detector, which detects thermal neutrons. One thing that's actually quite unique about this detector that we're actually studying right now, I'm not sure you guys know anything about thermal neutron detectors.
They covered it in the like the first day we were here. They told us the poster and like showed us like a background about it. We don't know it, but like we saw it earlier this week.
Okay. So just really quick, there's 2 types of neutron detectors. You have fast neutron detectors and thermal neutron detectors. It's really 2 groups, 2 camps. You have fast neutrons and thermal neutrons. One thing, so we built this thermal neutron detector, and then we had a little surprise with this detector, and in that we were getting higher rates than we expected, than we were expecting, and it turned out that this detector not only can detect thermal neutrons, it can also detect fast neutrons.
surprise!
And the reason and so it took us a little while to understand what the hell's going on. But so the way this detector works for thermal neutrons, you have a thermal neutron interacts with helium-3, proton triton generates a small amount of charge. We have a stopping gas inside this detector which prevents the charge from dissipating. We have a field. The charge drifts and eventually hits one of these pads. So this is a pad detector. So it hits one of the pads, we record the charge, and we get the energy, and we know we got that at one hit. The one thing we didn't expect was that the fast neutrons were interacting with our stopping gas. And what was happening with that, the fast neutrons hit the stopping gas, not the helium-3, which generated a recoil reaction and generated a track.
Charge. And then,
And based upon the length of the track, we can actually reconstruct the energy and then know what's going on. So, and the reason why this worked with this detector and not others, in most other neutron detectors, you have one wire, and so they have long wires in the X and long wires in the Y, and when an interaction occurs, your detector is quiet at that point in time. It's shut down until you read out the charge and come back. Here, all these pads are active. So one pad might be disabled for a single event. However, when you have this track, all the pads are active, and we can actually reconstruct the track. So this is something that we're currently investigating to see how we can exploit this. One of the issues we did find with this was that since we designed the ASIC specifically for the energy collected by a thermal neutron, we're a little the dynamic range for the readout for these fast neutrons is not sufficient. So a new ASIC will have to be developed. However, this is actually going in the right direction, where this might be the first thermal and fast neutron detector.
And you did it by accident. That's awesome.
Yeah, no, it's yeah, exactly. It's like we were like, where are those tracks coming from? You know, why are we seeing tracks? And yeah, no. So it's actually this was a very neat project. And the cool thing is this 1 meter detector can be read out with a single laptop going to an Ethernet port. So it's a really nice system and it's an easy system to read out for the final system. I should go a little faster. So the other thing we also designed here, besides the hardware, we also work on the software. So here you can see the Dune Wib with the Zinc UltraScale Plus with the cables. This is not the 25 meter cable that's used, but the short data cable to the ASIC board. And Jillian's currently working on the software to read out the system using Python in a server. So this allows us to do quick calculation tests for all the ASICs. It's going to be used for ASIC testing. So it's a quite a versatile system and it's very useful. Actually, I'll pass this one over to Jillian, since this was actually her first project she actually worked on here, and it's pretty much her.
Yeah, it's my baby. So I've been working with a grad student, I think maybe postdoc now, at the Center for Functional Nanomaterials, which is across the street. I don't know if you've been there, but he is specifically interested in DNA nanoassembly, which is like basically using pieces of DNA and heating them to certain temperatures to make them form little microstructures and crystals. And specifically the process that he needs to use for that is a process called temperature annealing, which is like heating stuff to like say 46 degrees Celsius for 2 minutes and then 50 degrees Celsius for 5 minutes, and doing this repeatedly until crystals form. And again, I'm not the biomedical expert on this, so I just know the temperatures that I need to reach, etc. So he'd been using a single system that was doing this that was actually meant for PCR, not specifically in like COVID PCR testing, but it's the same acronym, which means like heating stuff and using that to replicate stuff, but that can also be used for temperature annealing, and he wanted to be able to do this at a larger scale. So instead of just one at a time, being able to run multiple experiments at one time and being able to monitor them all on the same system. So what I did for him is I designed a PCB with actual heaters that are like printed on like a normal PCB, working very much like the same principles as a stove top. You know, you're running current through this wire and it heats up. On top of them are copper blocks that sort of absorb that heat and sort of keep it at a sort of consistent, more stable level that can transmit heat more easily to something that's sitting on top. I've got little sensors in there that feed temperature data back to an Arduino that plugs into the board, and that Arduino can modify PWM signals that go to an SSR like relay thing that modulates the amount of power that is being allotted to that heater. And there's a PID proportional integral derivative loop that, have you dealt with that?
Yeah.
Yeah, that's those can be a real pain, but it's sort of it can be very useful in like motors and like, you know, air conditioning and stuff where you're continuously trying to approach a temperature or some sort of speed smoothly.
You want to keep something in steady state.
Yeah,
It's a steady
Yeah.
state.
yeah, steady state, steady state stuff. Trying not to overshoot or undershoot too much. Still upgrading this system and trying to tune the PID loop.
So why did you use a PID? Why didn't you just use a bang bang? You just wanna make sure that it's at a steady temperature. So you want to turn it off, turn it on.
The bang bang was a little bit too. It wasn't smooth enough. Like
Yeah, a 0.1, they want to achieve 0.1 degrees Celsius
Yeah.
accuracy.
Mm-hmm.